Okay, we're in Unit 3 of AP Physics 2, and this unit's about electric force, field, and potential. So it's a big chunk of electromagnetism. Here are the 6 equations that relate to this unit, and with that, we can start with the content review. Okay, so before we talk about actual electricity and forces and things like that, we have to talk about atoms. And we're going to start with what's called the Bohr model of the atom. And that basically is a simplified model of an atom. It says there's a nucleus with positive and negative charges, protons and neutrons. And there's also rings outside the atom which has electrons. So there can be 2 electrons here, 1 electron here. This isn't a perfect model, of course. It's much more complicated than this, but this is a simplified model. We're mainly going to be talking about the electrons because they're negative charges and they're very small. They're on the outside of the atom, so they can easily leave the atom. And we do talk about moving charges here in electricity and magnetism. So it's mainly going to be that. We do talk about protons a bit because of current and things like that. We do talk about conventional current. Protons don't really move around because they're really heavy. They're right in the middle of the atom and they're bound by the strong force. But sometimes we do say they move, quote unquote, because that's how we used to think. We used to think that positive charges move, but it's actually negative charges that move in the opposite direction. But that's neither here nor there. We have to talk about conductors and insulators. Conductors are materials where electrons can freely move. So an example is metal like coins and paper clips. Electrons can move from one atom to another, just moving through the atoms and going to the other side of the material. Insulators, on the other hand, electrons cannot freely move around. They can move from one atom to another, but in a very limited manner. So an electron might move from here to the other side of its atom, or maybe even in an extreme scenario, it might jump to another atom, but it's not going to be moving from one end to another. Maybe one end to another of a single atom, but not of the entire material. So this is going to be usually plastics and rubbers. So charge carriers in general are just positive or negative charges. So it can either be a proton or an electron, and they make up objects. Neutral objects have equal numbers of protons and electrons. Negatively charged objects have more electrons, and positively charged objects have more protons. And the way you can charge an object, let's say you have a balloon, for example, the way you charge it is by adding or removing electrons. You can't really add or remove protons because, like I said, it's really hard to move them. Instead, it's electrons that are moving. So you can add, if this is a neutrally charged object, you can add an electron or you can take away an electron and it'll change its charge. And the charge of one of these particles is called the elementary charge. The charge of an electron is negative 1.6 times 10 to the power of negative 19 coulombs. Coulombs is the unit for charge. And for a proton, it's just going to be the positive of that because protons are positively charged. And you probably have heard of this before, but opposite charges attract, like charges repel. So 2 protons or 2 electrons are going to repel from each other. A proton and an electron are going to attract each other. And there's also the fact that charged objects always attract neutral objects. So if I have this charged object here and just a neutral object here, there is going to be an attraction. And electric current. So I kind of talked about this a bit before, but electric current is just the flow of charge through charge carriers. Now, actual current is the movement of electrons, and it moves in some direction. And we have current, I is equal to the change in charge over a certain amount of time, so how much charge moves in. But we generally talk about conventional current, and that is where positive charges move. So it's going to be the opposite direction. And the reason why we do this, it's not physically true. Positive charges don't move. It's the negative charges that move. But the reason why we do it is because Ben Franklin thought that positive charges moves, and he laid the entire foundation for electricity on this belief. So just for convention's sake, we use conventional current. But you should know, in reality, the actual current is in the opposite direction, where electrons move. And the movement of actual electrons is random. It's not just like all electrons are marching one way. It's random movement. So if you have one singular electron, it moves in some random way. It can even go backwards. But overall, the net effect is that it moves forward in the direction of the actual current. And this slow velocity it has is called the drift velocity. It's very slow compared to the actual current. The actual current is just a group of electrons that all have this random motion directed one way. But the drift velocity is just a singular electron's random movement, very slow, even. And this is going to be important when we're talking about electric circuits, which we're mostly going to be talking about next unit, but it is good to know about electric circuits. Okay, so we talked about electric charge. We need to conserve it though. Just like with energy and mass, we need to talk about conservation of electric charge. That means that charge can neither be created nor destroyed, and the net charge in a closed and isolated system will always be constant. Now, just like temperature in our last unit, electrons move from high concentration to low concentration. So if you have two objects that touch, one has a lot more electrons than the other. Electrons are going to move from one object to the other, assuming they're conductors. If they're conducting objects, then it moves, because like I said, in conductors, electrons can basically move anywhere in the object. If they're insulators, it won't really move. It'll just attract towards the other object. So if you have two identical spheres in contact, it would evenly split the charge among them. One has 4 coulombs of charge, one has 2 coulombs. It'll become 3 and 3 each. So charge distributions within objects. We talked a bit about that right now, but we need to talk about how to know if an object is charged or not. If you have an unknown object and you see that it repels another object, that means both objects are definitely charged, because repulsion only occurs when like charges are there. Attraction can occur if one of them is neutral or if both are opposite charges. So you don't know about attraction, but if two objects repel, you automatically know both are charged and they both have the same type of charge. You don't know which one, but you know they both have the same type. The reason why neutral objects are attracted to charged objects. So if you have a neutral object here, and you have a charged object here. So this has more electrons than protons, which means it's negatively charged. The thing is, these negative charges and these positive charges attract, while these negative charges are repelled. So the positive charges don't really move. They can be anywhere here, but the negative charges go to one side, the opposite side, while these negative charges move to this side, and this positive charge stays here. And so this is what's called polarization, where the overall charge is neutral in this object, but one side is slightly charged and the other side is also slightly charged. So even though the protons don't physically move near this side, there's a lack of electrons on this side of the object. And that's why these two attract each other, because there's this attraction force between them, and this repulsion force is pretty small because this distance is farther. And we'll talk about the exact formula for the force later, but it does have something to do with distance. The farther you are away from it, the less force you feel. And so this attraction force is closer than this repulsion force, and so the net result is that they attract even more and more. So there's a few ways to charge objects. Induction is probably the most complicated one, so we're going to start with that. Induction is when you don't touch the object. Let's say you have a negative charge, a negatively charged object, and you have a neutral object, just like our last scenario. What you want is you need to connect a ground to this neutral object. And this is the symbol for a ground. A ground is basically like a really big object that adding a few electrons or removing a few electrons has basically no change on its net charge. So an example is the Earth, which is why it's called the ground. Another example is your body, because you just have a lot of charges in you. Adding a few may shock a little, but it doesn't really change your net charge. Like, could be like +3 electrons, but as a percentage of the entire number of electrons in your body, it's barely anything. So what you're going to do is you're going to use this polarization principle. You're going to bring this charged object near this uncharged object, and your negative charges are going to move towards this side. Your positive charges are just going to stay there, but these negative charges want to get away from this because they're being repelled. So you might think they go to this side, but actually, since there's this ground, the negative charges just escape onto this ground. They leave this material completely, and now you remove the ground, and then you take away the object. If you take away the object first, then the negative charges would come back because they're attracted to these positive charges here. And so first you have to remove the ground, just disconnect it. That means the negative charges cannot come back, and then you remove this original object away. And now this is charged with the opposite charge. If you bring a negative object close and through induction, your new object is going to be positively charged. So it results in an opposite charge. Another thing is charging through friction. So when you just slide through two objects together, you could charge an object because of an electron transfer when you're sliding two neutral objects. So if you have like a rod and a cloth, which is the usual example, you can just rub them together, and this is because of electronegativity, which is an object attraction to electrons. And a more electronegative object will gain electrons, less electronegative object will lose electrons. And as you might expect, this results in opposite charges because charge is conserved. So if you have to add electrons to one side, you have to lose them on the other side. So they're going to be opposite charges in the end. And finally, there's conduction, probably the easiest way to think about it. We talked about this before, didn't formally say it, but it's when two objects are in physical contact. You charge an object by touching it. You have a charged object, and you have a neutral object, and you just touch them, and charges flow from one to another, from high concentration to low concentration, and the result is two objects that are of the same charge. So you can use different methods for different results. If you want the same charge, you have to do it through conduction. If you want opposite charges, it depends on what you start with. If you start with two neutral objects, you can do friction. If you start with one neutral, one charge, you have to do induction. So it's good to know those three different types. Now, what about charge distribution in insulators versus conductors? So in an insulator, the net charge stays at the charging site. So if you have an insulator here, and I know I've been drawing spheres this entire time, or circles because it's a 2D plane. You can have anything, a sweater, a balloon, anything. I've just been drawing spheres because they're easy to draw. If you have an insulator here, and you charge it through friction, for example, the charges stay here. The net charges stay here because it's really hard to move around in an insulator. These electrons can move to one side of an atom, but they cannot just move to the other side of the material. On the other hand, if you have a conductor and you have these original positive charges and you charge it negatively, these electrons want to get as far away from each other as possible, and they can do it because it's a conductor. So the net charge spreads evenly in a conductor. And just like we talked before, there's polarization. Let's talk about polarization with conductors, which we just did. That's when all the electrons go to one side, and the positive charges, the protons, stay where they are. But in an insulator, it's a bit different because, like I said, the electrons can't just move from one side to another. So they go to their own side of the atom, a specific side of the atom. They all point in one direction of their own atom. So if you zoom in a bit, all the atoms would have a nucleus here and the electrons on this side. And if you just add up all of those, the net effect is a slightly weaker polarization, but polarization nonetheless, because all the electrons are on one side of the atom. They're not on one side of the material, but rather one side of the atom. So I'm trying to drill it in your head, difference between insulators and conductors. There's this constant called electric permittivity, denoted with an epsilon. And that's basically the measure of resistance of the propagation of the electric field. That's waves. We'll get into that chapter 6. But it's basically saying that it's kind of resisting electric fields, which, of course, we haven't talked about yet. But it's pretty big in electricity. You'll see this constant a lot. Specifically, epsilon naught, this E0, is vacuum permittivity. So it's the electric permittivity of the vacuum, and this is approximately 8.85 times 10 to the power of negative 12 coulomb square per Newton times meter squared. That's a really weird unit, but the formulas we'll see, you'll understand why that unit is that. And the reason why this occurs is because when you're in when you have some matter between you and between charges, this electric permittivity is the resistance due to an opposing electric field. And that probably doesn't make much sense now, but it'll probably make more sense when we talk about electric fields. Another thing is called the dielectric constant, and that's related to the electric permittivity of a material. This is of a vacuum, but the electric permittivity of a specific material is the dielectric constant of that material times the vacuum permittivity. So this kappa changes from material to material, and when you multiply that by epsilon naught, you're going to get the electric permittivity of that material. And this is pretty big when we talk about capacitors later. Okay, finally we get into the namesake of this unit, electric force, field, and potential. We're going to start with force. Electric force is the force due to electric charges. Protons and electrons have the same force because they have the same charge, but protons do have a less acceleration because of their heavier mass. So important things to note there. Again, every time we're talking about forces, we're talking about free body diagrams. So this time we're adding electric force to our list of forces, and that can be in any direction depending on where the attraction or repulsion is. And electric force is going to follow what's called an inverse square law. I hinted at this a bit before, but it's going to be negatively impacted by distance. The farther you are away from a charge, the less force you have. And it follows this type of relationship. It's 1 over r squared, where r is the distance. So not just 1 over r, but 1 over r squared. It gets pretty weak when you go really far away from it. And this alpha symbol right here, that just means proportional to. The actual equation for electric force is called Coulomb's law, and it's 1 over 4 pi epsilon naught times q1 q2 over r squared. And this quantity, 1 over 4 pi epsilon naught, is just equal to what we call K. K is just the electric constant, and it's KQ1 Q2 over r squared. And this is pretty similar to the gravitational force equation. That's G m1 m2 over r squared. Really similar, actually. And that's because there's also a gravitational field force, this is an electric field force, and things like that. So there's a lot of similarities with gravitation. But this K value, you can derive it because it's just 1 over 4 pi epsilon naught, and you know epsilon naught, and things like that. It's also given on the equation sheet, so don't worry about it. And when you have multiple charges, it's going to be the vector sum, because electric force is going to be a vector. So you need to know how to add electric force through vectors. We will be doing a practice problem about that in the future, though, so don't worry. Now, I just talked about how gravitational force is very similar to electric force, but there is a bit of a difference. When you have big objects like planets, stars, the gravitational force is going to be dominant, even if there's a net charge on the planets, a very small net charge, because the sheer number of electrons and protons just make it so that you can't have an insane amount of net charge. The gravitational force is going to be dominant because of the huge masses involved. But if you have microscopic situations like electrons, individual electrons, or even just like a wool sweater and a rod, right? Electric force is going to be dominant. That's not usually considered microscopic, but in the grand scheme of things, it is microscopic. Compared to the universe, compared to planets, like a wool sweater is considered microscopic. Another thing is gravitational force is only attractive, but electric force can be either attractive or repulsive depending on the different charges. So that's also pretty important to know. Finally, we're getting into fields and potential. So electric field is basically electric force per unit charge. So this electric field E is equal to Fe over Q. That is the formula for electric field, and that just means it's going to be equal to 1 over 4 pi epsilon naught times Q over r squared. Now, this is where it gets a bit confusing. This is Q1, Q2. So another way you can write that is big Q, little q. That means, that kind of implies that this big Q is bigger, like has more charge than that, which is not always true, but I'm just trying to differentiate like the main charge versus another charge. So think of it like the sun and then the planet orbiting it. You think of the sun as the big mass and the planet as the small mass. Kind of like that here. You have a big charge, not necessarily big as in like it has more charge, but it's just what you're focusing on right now. And then there's another charge in the vicinity, and the electric force between them, you're focusing on this one. So the electric force is going to be the same since Newton's third law, but the electric field that this object feels is independent of this object's charge. Instead, it only depends on this bigger charge, or this leading charge, I would say. And that's what this is here. So I can replace that with a Q, a big Q. This we usually call a test charge because we're testing the electric field at a point. It doesn't matter what the charge of this test charge is. It's usually going to be a proton because we just like positive charges in physics. I don't know why, but it's usually going to be a proton. But it doesn't matter what that charge is because the electric field would be the same for any test charge you put over there. The electric force would not, because that depends on this test charge Q, but the electric field would be. So important to distinguish that. An electric field diagram basically represents the electric field that a positive test charge would feel at a certain distance. Like I said, we just like positive charges in physics. So if you have a positive leading charge, I would say, your electric field lines are going to point away because a positive test charge would be repelled by this. And so it looks something like that. You're just going to continuously go away. At no point is it going to be coming back towards you. And if you have a negative charge, it'll be the opposite. A positive test charge would be attracted. So I'm just going to draw fewer lines here. That doesn't mean that it's weaker in any way. It just means that it's just going to be similar. And in this type of diagram, the lines show the direction that a positive test charge would move, and the density of lines show the strength of the electric field. So closer to this, it's going to be more dense. As you can see, it's kind of farther apart out here. Closer to the actual charge or the leading charge, it's going to be more dense and so therefore stronger. Farther away, it's going to be weaker. And then there's also electric potential. So while electric field is vector, just like force, there's going to be electric potential V, which is scalar. And that is electric potential energy, which is UE per unit charge over Q. And that you can write as 1 over 4 pi epsilon naught, which, by the way, you can just replace this with K. But it's going to be this times Q, probably big Q, over R. Note that this is over R, this is over R squared. Just something to keep in mind. And another formula you should know, this just plays on what I just said. This is R squared. V is equal to E times R. There's a bit more calculus involved in this, but basically in AP Physics 2, it's going to be the electric field times the distance. So you can calculate, just like how we can calculate the strength of an electric force, but you can also do that for electric field. Again, it's a vector sum for that if you have multiple charges. For potential, though, it's going to be just a regular sum because electric potential is scalar. On a conducting sphere. Okay, this is pretty interesting. If you have a conducting sphere, there is no electric field inside the sphere. That's because electrons want to get as far away from each other as possible. So they're going to be on the outside. That's the highest surface area, so they're going to be on the outside. And there's going to be no electric field inside. Once you get out, though, then it follows this law, the inverse square law. So the graph of it is practically going to be 0 down here. And then once you get to the actual radius of the sphere, after that, it's going to decrease based on the inverse square law. So pretty interesting there. And now we finally talk about capacitors, which we're going to talk about a lot more in the next unit. We're just introducing it now. So a parallel plate capacitor is basically two plates here. One is positively charged, one's negatively charged. And so there's an electric potential between them. There's a potential difference specifically, delta V, between them. And that means that there's energy stored, and that energy is stored in the form of an electric field. You have more electric potential when you're near the plates, because if you're a positive test charge, for example, and you're near the negative plate, then based on the inverse square law, the closer you are, the more force you experience. So you're going to accelerate towards the negative charge. And you're also being pushed by the positive positive charges on the positive side of the thing. So it's basically two forces acting on you in the same direction. And one nice thing about parallel plate capacitors is that the electric field between the plates is going to be uniform. It's going to be the same magnitude and direction at all points. We can talk more about electric potential now through isolines. Isolines is kind of like electric field diagrams. It's another way to visualize the distortion of space due to a charge distribution. And this is through potential. There's let's say you have a positive test charge here and a negative test charge here. And you want to find the electric potential. Well, at the center, it's going to be 0 volts because because you're not going to be moving in either direction. There's no potential energy there. But as you get closer to one side, there's going to be rings that show you what the electric potential is there. If you've ever seen a topographic map of a mountain or something, you see rings around here that show the different elevations. This is basically that. The elevation in this case, though, is the potential that a test charge has in near the region of another charge. And this elevation map shows the gravitational potential. This shows the electric potential. And so lines, the isolines are of equal electric potential, and between each two lines is going to be equal increments of electric potential. And just like with electric field diagrams, closely spaced lines have a larger electric field. Now, when you're near a certain charge, the sign of the potential is going to be the same as the sign of a charge. And points of 0 potential are infinitely far away from the charge if there's only one charge. But here we have two charges, so it's going to be right in the middle of it. One way you can relate electric fields and potential is that the electric field is going to be perpendicular to the isolines, pointing towards the more negative region, or more negative electric potential region. So it's going to be perpendicular here, pointing outwards, because this is where it's more negative here. It's very positive here. It's less positive here, so more negative. And so your electric field will be perpendicular to the isolines and pointing towards the negative area. And you can find the electric potential of a point using the nearest isoline. If you have a point here, you just look at the nearest isoline, and that's going to be close to what the electric potential will be. If you want to find the potential difference, it's going to be subtracting the electric potential. So if you have 2 points here, there's going to be a potential difference. You just subtract the two potentials. And it's going to be positive if it's from high potential to low potential. So going from close to the charge to away from the charge is going to be a positive potential difference. And negative is low to high. So if you're going away from the charge and towards the charge, that's going to be a negative potential difference. Finding the electric potential energy at a point. Okay, that is going to be multiplying the electric potential, which we find by using the nearest isoline, by the charge of the object at that point. So then you do need to know the test charge, actual charge. And finding the electric field, like we said, is just using the direction that's perpendicular to the isoline and then pointing towards the lower potential or the more negative potential. Now, uniform isolines occur in a parallel plate capacitor, so they're going to be just straight lines that have the same potential. And sometimes you say 0 potential is right between the plates. That's usually what you say. Sometimes you say it's one plate or the other. And finally, last topic for this video. I know it's a really long video. It's a lot of topics to cover. It's conservation of electric energy. We talked about conservation of electric charge. Electric potential energy, UE, is just equal to Q times V, the electric potential, which is also QER. So that's another formula for it. And it follows the conservation of energy if the electric field is included in the system. If there's an external electric field, then no, it doesn't. But this basically says that UEI plus KI is equal to UEF plus KF. Because initial potential energy plus kinetic energy is final potential energy plus kinetic energy. And so you can calculate the velocity that a certain charge has at one side of the plate, starting at the other side, using the difference in the potential difference, basically, the difference in electric potential energy and the mass. That gives you the velocity because this is 1/2 mv squared. So like I said, that's the end of this unit, but we do have a few practice problems to go through. So this first one, like I said, we will be using vector sums for forces, and this is an example of that. It says there's 3 microcoulombs. This is a micro right here. We need to be sure to remember that that's micro and not just coulombs. And there's a 3 microcoulomb here, 3 microcoulomb here. What we're going to need to do is multiply it because it's asking for the net force on here. First, we're going to calculate this net force. That's going to be equal to 1 over 4 pi epsilon naught. Okay, first let's calculate what that is. We know epsilon naught is 8.85 times 10 to the power of negative 12, but let's find out what k is. that is going to be, you just plug it into your calculator, or you can look on your equation sheet. It's going to be 8.99. So this k value is going to be 8.99 times 10 to the power of 9. It's pretty close to 9 times 10 to the power of 9. You can use that as well. So instead of this, we can just do k q1 q2 over r squared. Q1 here is going to be, so we can actually replace what we know. It's 8.99 times 10 to the power of negative 9. That's the value for k that we just found out. And then we have to multiply by the charge, which is 3 microcoulombs. So 3 times 10 to the power of negative 6. Oh, and this should actually be a positive 9, because while epsilon naught has a negative exponent, k is 1 over epsilon naught, which means it has a positive exponent. So micro is 10 to the power of negative 6. So we multiply that by that. And then this is negative 4. You just use the absolute value of the charge, because the positive or negative you can find using direction. You know this is going to be attraction because they're opposite charges. And so this is over r squared. R, the distance between them, it says 1 centimeter, which is also not nice units. We have to do 1 centimeter times 10 to the power of negative 2 to get how many meters it is, and you have to square it. So plugging it all into your calculator, one useful tip actually for things like this is the E button. Your calculator might have an E button, and that basically tells us it's basically a shortcut for times 10 to the power of something. If you do 1e negative 2, that's going to be 1 times 10 to the power of negative 2. You plug this all into your calculator, you get 809.1 newtons. And it is newtons, not any other unit, because we converted all into proper units. We did coulombs here and meters here. And then we have to do the same force here. It's actually going to be the same exact force and same charge, same distance. So it's also going to be 809.1. And if you look at it, you add them, you get 1618.2. That's not any of the answer choices. Did we do something wrong? Not quite. We didn't do anything wrong with the force calculations. It's just that since it's a vector sum, you have to do Pythagorean theorem, basically. It's a very nice vector sum. You don't actually have to find the components of the vector in this case, but you do have to do the Pythagorean theorem. And you're going to get 809.1 squared plus 809.1 squared, and the square root of that. And that's going to give you approximately B as your answer. Okay, moving on to the next question. This is about capacitors, and it says there's a parallel plate capacitor, there's positive charge here, negative charge here, there's a dielectric. We did talk about dielectric, not exactly in the context of capacitors, but we did say that the dielectric constant of a material is its change from the vacuum. We don't really care about the dielectric here. It's just what occupies this in here. It's just an insulator between two capacitors. It says, where's the energy stored in the capacitor? Outside of the metal plates is just here. Inside is like between the dielectric material and the plate. On the outside surface of the dielectric slab, that's kind of similar, but it also includes this surface. And then on the inside, that's just within the dielectric slab. And we know that the energy stored is going to be in the electric field, and that's going to be pointing in this direction. Well, if you were to use a positive test charge, it would be in this direction. But all that matters is it's going to be going from one plate to another. That means it's going to be inside the dielectric slab, because it's virtually going inside the slab. If it was just air, it would go from one plate to another through the air. Here it's going to be going through the dielectric slab. So it's going to be inside that. And another type of practice with charges and vector sums. First, we have to find the electric force felt by charge 1 due to charge 2. So we're not given any numbers here, so we just have to plug stuff in. We're given that the force equation is KQQ over R squared. You can do Q1, Q2. I'm just doing QQ because there's one main charge that we're focusing on. We're focusing on charge 1. And so this is going to be equal to K times this is plus Q, this is plus 2Q. Over the distance between them is A plus 2A, which gives us a total of 3A. So 9A squared, because we have to square it. And when you simplify it, you get 2 KQ squared over 9A squared. And that's going to be your electric force. I can probably write that here. That's going to be the electric force on charge 1 due to charge 2. It also says the direction. You can just say they're going to repel from each other because they're both positive charges. So it's going to go upwards. So I'll probably just add that here. Part B, find the electric field at the origin created by both charges. And so let's look at the first charge. Electric field, E, is going to be F over Q. So it's just going to be KQ over R squared. And we have K. We have Q is just positive Q. R is going to be just A because it's just from the charge 1 to the origin. So A squared. So that's going to be KQ over R squared, which is just KQ over A squared. So that's electric field of 1. Electric field of 2 is going to also be KQ over R squared. But when we plug it in this time, it's a charge of 2Q. But it is a distance of 2A. And when you square that, you get 4A squared. And that's equal to 2KQ over 4A squared, which is just KQ over 2A squared. And now, what directions are the electric fields? If we put a positive test charge here, it's going to be repelled away. And if we put a positive test charge here, it's going to be repelled away from this as well. And so if you see, this has a bigger denominator, which means it's a smaller electric field. And so the net electric field will be downwards. Now, what would be the magnitude of it? Well, since it's a vector sum and they're going in opposite directions, you don't add them, you actually subtract them. So you have KQ over A squared minus KQ over 2A squared. And you can find a common denominator of 2A squared, which means you also multiply the numerator by 2. You get 2KQ minus KQ. It just gives you KQ over 2A squared. So your electric field will be KQ over 2A squared downwards. Okay, and that's pretty good. We just did A and B. There's also C and D though, and this video is already pretty long, so I'm just going to cut it here. C and D though, I do want you to try on your own. It's a bit more difficult, which is why it's a good practice for this. It's more algebra based than actually physics based, but yeah. So good luck on C and D, and I'll see you in our next video, which is Unit 4, Electric Circuits. See you next time.